Do you ever have a great idea? One of those that wakes you up as you're just drifting to sleep and then keeps you awake for the remainder of the night? Does it involve stuffing custom electronics into random, inane objects around your home? If so, you and I are probably a lot alike. And if not, then, well, that makes you a normal human. Anyway, one of those middle-of-the-night, jolts-you-awake, silly ideas I had has led me to build a custom glass tile backsplash, with each tile having an individually controlled RGB LED and touch feedback. It's a sort of low-resolution touch display, but for your kitchen wall. I've built some hardware to add to the tiles to make this happen, but now I need to develop the software. As with any of my software projects, step one is a quick Google search to get some ideas, maybe some Stack Overflow, see what's out there. All right, backsplash programming. Well, this isn't great. Yeah, show results with programming. Yeah, that's what I want. Backslash, yeah, okay. Wait, what's this? Well, that was a cool project, but it's definitely not what I'm doing. It's looking like I'm on my own for this one, so we might as well dive into it. I'm Zach. You're watching Zach of All Trades. If this is the first time you're joining me, there's a whole video on this concept linked in the description. To give a brief recap, I'm going to attach a small circuit board to the back of each tile with an addressable LED, better known as a NeoPixel, that will shine into each tile. There will also be a microphone coupled to each tile to tell if that tile has been touched. Each addressable LED has a data in port and a data out port, and they work by stringing them all together so that the brightness data goes into the first LED. Once it's had its fill of data, it will forward anything else it gets on. Every LED in the string does this, meaning that only one wire is needed for the whole string's data. To get the microphone values back to the main controller being the processor that actually controls the LEDs, I'm using small microcontrollers on each circuit board. These will read the microphones using their analog to digital converters, calculate the signal amplitude, and then return that value to the main controller. It will do this over an extra wire that is shared between all of the tiles in the string. In order to time this and ensure that only one microcontroller is talking at a time, I'll be sending the microphone values back only when the LED sees its first signal edge. Since the LEDs each get their signals at different points in time, in the order of how they're strung together, the microphone response values should also be in that order, provided they occur quick enough. I hope that makes sense. If not, feel free to go back and look at the other video where I explain this in more detail. This video is going to focus on programming the small microcontrollers that go into each group of 2 tiles. That is, the distributed processors all over the wall. Programming the main controller, which will command the LEDs, is actually not all that interesting. There are many tutorials on how to program NeoPixels for all kinds of different processors on websites like Adafruit, even DigiKey. Basically, you use a timer peripheral in pulse width modulation mode, PWM mode, to send a clock signal at the required data rate, 800 kilohertz for my case. You encode the data right into the clock by shifting the clock's duty cycle. That is the ratio of time the clock is high and low in each cycle. This is all laid out in the LED's datasheet. Save the values you want into an array in your code, then send them to the timer peripheral using a direct memory access peripheral. That's pretty much it. You of course have to decide what colors to make the LEDs for whatever the desired effect is, but this can be as simple or as complicated as you want, and it's a whole nother topic. Make sure to subscribe, because once the wall is all built, I'll be putting a video together on coding the main controller to make interesting effects. This project is going to require a lot of microcontrollers, at least 160, probably even more than that. So I needed to specify something cheap. I chose the Puya PY32 Microcontroller, which is a familiar Cortex M0 Plus part. I found this from Jay Carlson's blog. He described them as the 10-cent microcontroller, which I actually found to be pretty spot on price-wise. I've encountered a few minor issues with these, but overall, they're working as expected. I'm not covering the PY32 directly in this video. I'm going to do a whole separate video on that. But I'll mention a few relevant things here and there as I need to. This probably sounds obvious, but the first step to writing software is figuring out what the software should do. So what do these little Puya microcontrollers need to do? First, they need to read the microphones to detect the sound wave in the tiles. Sound waves are oscillatory, so to determine how loud a tap is, I need to find the amplitude of the signal by taking the difference between the maximum and minimum signals. The PY32 then needs to save the greatest amplitude it calculates over a given period of time. For this project, that time period is the refresh rate of the LEDs, since I only send values back when the LEDs get new data. The PY32 needs to send that value back to the main controller at the appropriate time, so that the microcontroller receives the responses in the same order that it is commanding the tiles. To do this, the PY32 will monitor the LED command signal and return the greatest microphone amplitude as soon as that LED signal appears. This seems pretty simple, but there are some subtleties. And that's it basically, except each microcontroller needs to do this for 2 LEDs and 2 microphones. To program these, I'm using Keil MicroVision as the IDE, available right from ARM. You'll need to get a pack for your microcontroller, which I found was included with the MicroVision install. I'm flashing the code and debugging using a knockoff ST-Link V2 debugger. These $10 knockoffs have proved to work great for this. The first step, at least for me, was to configure the peripherals. I did this sequentially, configuring one, verifying it worked with simple code, then moving to the next. For this project, I ended up using 3 timers, the Universal Asynchronous Receiver Transmitter, or UART, for the serial communication between the PY32 and the main controller, the PY32's analog-to-digital converter, ADC, and the reset and clock control, or the RCC peripheral, which was needed to configure the clock. I also relied heavily on interrupts in this project, that is, pieces of code that are jumped to in real time based on another event, such as an external pin changing or the ADC finishing its conversion. As soon as that event happens, this separate code is called, provided there aren't any conflicting or higher priority interrupts. Anyway, I had to configure these as well, but that's also relatively straightforward. I'm not going to go into detail on configuring the chip, other than recommending 2 sources of information to help you out. First, the PY32 is coded nearly identically to the Cortex-M0 Plus STM32 parts. If you search for what you're trying to resolve, but you search STM32 instead of PY32, you're pretty likely to find the answer you need. Now, STM has configuration tools, and those aren't going to apply here. Many tutorials are going to talk about those, but if you can find the source code, you can just reference that. The manual for the STM32 hardware abstraction layer, or the HAL manual, is also an excellent reference. Make sure you get one for the M0 Plus course. Second, there is a lot of example code provided in the documentation from Puya. Download the zip file from their website, unzip it, then go to Library and Examples, PY32F0XX Firmware v1.1.2, Projects, choose your appropriate microcontroller, and then open Examples. There you go, examples for each of the peripherals. I implemented this code in a timer and interrupt-based fashion. That is, in the while loop of the main function in the main.c file, there's absolutely no code. Just antiquated, commented out stuff that I'm afraid to delete in case I need it again. I might be a bit of a code hoarder. Instead of the main loop code, there are 2 timers implemented that periodically trigger events, and other functions. There's also an external interrupt implemented that triggers a specific piece of code when an external pin transitions. And that's pretty much it. The PY32F002A only has 3 user configurable timers. 1 advanced timer, 1 basic timer, and 1 low power timer. I ended up needing all 3 of these for this project. First, the basic timer, timer 16, is configured to trigger 2,000 times every second. Every time the timer triggers, it jumps to a callback function that tells the ADC to sample the microphones. This means I'm sampling the microphones at 2 kHz. Per Nyquist's sampling theorem, which states that you need to sample at twice the frequency you want to measure, I should be able to pick up frequencies up to 1 kHz, which is about B5 on a piano. It sounds like this. I believe this should be sufficient to pick up any taps on the tile. Now this chip only has 1 analog to digital converter. However, you could tell it to read from 1 of 9 different pins, and it can switch between them rapidly. So you can essentially measure 9 different signals, just not at the same time. So I wrote 2 little functions, one to select channel 1, the other to select channel 2, and these are how I've wired it on the circuit board. I simply switch the channel, measure, switch the channel, measure. for each microphone, 2,000 times a second. I then take the readings. I see if the reading is greater than or less than the previous largest and smallest values, respectively. If they are, I save it as the new greatest or lowest value, and then I recompute the amplitude by taking the difference of the two. To get the microphone amplitudes out of the PY32, I implemented two external interrupts. One of these watches the signal input to the first LED, the other one watches the signal input to the second LED. As soon as the microcontroller sees the voltage go from low to high, it jumps in the code over to a portion that sends the appropriate values back to the main controller. It's pretty simple. Just send the save amplitude over the UART. The UART here is set pretty fast, 921,600 baud, so that the signal can be sent in time. This return value is also only 8 bits. Remember, this signal needs to finish sending in the time it takes the main controller to send 24 bits to command the respective LED, or it could overlap with another message and be unreadable. I ran into an unexpected issue here, although in hindsight it was kind of obvious. The interrupt code to send the ADC value would finish before the 24 bits to command the LED had finished. The interrupt would then trigger for a second time, duplicating the message. Now this isn't what I want. I need it to only send the ADC value one time, the first time it sees any signal. To implement this, I did some trickery using the other two timers. The general idea is this. When the interrupt triggers and sends the ADC value out, I set a flag that basically says already sent, and it locks out that interrupt code from repeating until that flag is cleared. The harder part is figuring out when to clear that flag. If you watched the previous video on this project, or if you've worked with NeoPixels in the past, you may recall that to reset the LEDs, and to send a whole other block of data, you need to hold the clock line low for 200 microseconds. I want the reset flags to clear when this lull occurs. To find this, I'm going to use the other two timers. The low power timer, which is very basic and isn't really meant for this, I just ran out of other timers. Well, I'm using it to set a time period during which to check for signal edges. The LED signal will stay low for at least 200 microseconds. However, I can't guarantee that my sampling window will line up with the beginning of that 200 microseconds. Therefore, just to be safe, I set the period to 100 microseconds. That way it doesn't matter exactly where that window is in the larger 200 microsecond window. There should always be 100 microseconds where no signal edges occur. I just count the signal edges in each time period. If there are none, that is, I count 0 edges, then I must be in reset and I can clear the flags. That's it. But how do I count pulses? It turns out that this is easy as well, using the Timer 1 peripheral, which is a fully featured advanced timer. To do this, I'll use the external trigger, or ETR mode. This allows the timer to count on an external signal, the input of which is an alternate function on one of the microcontroller pins. Every time that pin rises, the timer will count. So I just use this mode to count each edge in the 100 microsecond window, as defined by the low power timer. When the low power timer triggers, that is, it reaches the end of its window, I reset this counter. If this counter counts 0, reset the flags. Now, this ETR trigger pin is only mapped to one external pin on the microcontroller, and I wasn't originally planning to use this mode. So when I made the circuit boards, I didn't wire it up correctly. Now, if you watched the last video where I discussed making the boards, you might remember that I broke out the extra pins to test points, just in case. Well, I got really lucky here, because one of those unused pins was the ETR pin. So I was able to just add a small white wire to get the LED signal where I needed it on the microcontroller. Once I got this white wired and the code implemented, I checked it out on the oscope. Here are the results. You can see the LED signal here in yellow and the return ADC values in blue. It looks great, and I'm optimistic that this is going to work in the full implementation. Here's a shot of the test apparatus I made from one of the circuit boards and two tiles, with a simple 3D printed ring around the outside. I'm using this to prove everything out, and so far it looks like everything's working well. It's exciting. Just imagine 160 of these all side by side working in unison. That's it for coding these, and for this video. Be sure to like and subscribe if you want to see more.